Thank you, John Lee. I was pleased when Jean Louis asked me to introduce to you John A. Focht Jr., the 29th Terzaghi Lecture, and the first speaker this afternoon. John and I have been close associates for more than 40 years, so I can and do lay claim to special insights about this distinguished engineer. Mr. Focht is most widely known for his outstanding service to the American Society of Civil Engineers. Most of this audience is aware, I'm sure, that he became national president of the ASCE in 1989. Prior to this, he was president of the Houston branch, then of the Texas section, and in following years he was director from District 15, then vice president of Zone 3. All of this before becoming the Society's president-elect. In addition, he's always been closely identified with the Geotechnical Engineering Division of the Society, serving on many of that division's technical committees, as well as the Executive Committee, ending as its chairman. Equally impressive, however, and possibly of more personal interest, especially to me, is Mr. Focht's distinguished engineering career. Appropriately, this began in 1941 when, as a freshman in civil engineering at the University of Texas, John sat in on most of the lectures given that year by Dr. Karl Terzaghi, who was in residence there at that time. This exposure to the father of modern soil mechanics led John first to Harvard University as a graduate student, and then to a successful consulting career in geotechnical engineering. After leaving Harvard, John joined the U.S. Waterways Experiment Station, where he worked with an elite group of engineers, at that time dealing with the foundation features of major flood control projects along the lower Mississippi River. Then, after 2 years active duty in Korea, where he led a construction engineers battalion, it was my good fortune that he joined forces with me in Houston in a consulting engineering company then called Greer & McLelland, which a short time later became McLelland Engineers. Almost immediately, John assumed the primary technical role in that company, and for the next 40 years provided technical leadership to a growing international practice in geotechnical engineering. Several outstanding qualities characterize his leadership during this period, and I'll mention briefly just 4. First, he repeatedly demonstrated his skill as a technical innovator. He pioneered, for example, the nonlinear analysis of laterally loaded piles and pile groups by introducing concepts still essential in today's design of offshore structures. And he developed the rational methods for supporting and controlling settlement of high-rise buildings on deep soils, an essential component, as it turns out, in the design of tall buildings that make up Houston's central business district. Second, John has always flourished as a technical collaborator. I don't think he's ever as happy as when he's pooling his skill and his experience with the input of other experts in resolving the design problems faced on major projects. His work on the spillway foundations for Lake Livingston Dam on the Trinity River come to mind, where he was involved with extensive collaboration with Arthur Casagrande and the water resource engineers of Brown and Root and Forest and Cotton. Third, he's been an outstanding teacher and role model for 2 generations of young engineers, patiently guiding their efforts, sometimes correcting their mistakes, always providing a role model. Fourth, he's been a strong contributor to the profession's technical literature, being the author of over 40 papers and book chapters. The impact of his writings is attested by the fact that of the 5 papers he submitted to the prestigious Journal of Geotechnical Engineering not only were accepted for publication, but all 5 won national awards. This included twice the Middlebrooks Award. This is the Geotechnical Division's top publications honor, the James Laurie Prize, and twice the State of the Art in Civil Engineering. It's not surprising then that the University of Texas designated him a distinguished engineering graduate in 1964, and that the National Academy of Engineering elected him to membership in 1987. I'm sure, ladies and gentlemen, that you will profit from his experiences and observations, as told in his lecture, Lessons Learned from Missed Predictions. John?
Thank you, Bram, and thank all of you for coming. I sincerely appreciate the invitation from Jean-Louis to repeat my Terzaghi Lecture here at A&M, particularly on the occasion of the second Spencer Buchanan Day. This lecture was the 29th in the series honoring Dr. Karl Terzaghi, as Bram mentioned, the founder of modern soil mechanics and foundation engineering. The paper was first given at the ASCE Convention in Dallas in 1993. I'll focus on the broad issues involved in the prediction process that affect the quality of our predictions of the geotechnical performance of completed structures. Only limited attention will be given to redefining or refining technical aspects pertinent to our professional practice. It's important to recognize and acknowledge that the practice of civil engineering, and geotechnical engineering in particular, still remains as much art as science, perhaps more, but certainly combines both. I hope that this lecture will be a benefit to all levels of geotechnical engineers, from the very computer literate recent graduates to the graybeards among us and other civil engineers as well. Looking back at the contents of the prior 28 Terzaghi lectures, 4 had a major philosophical theme. 3 more had strong philosophical overtones. The remainder were concerned with technical topics: projects, theories, problems, and solutions. My intent is to add to the philosophical background that was started by Casagrande with his lecture, The Role of the Calculated Risk in Earthworks and Foundation Engineering, followed by Jerry Leonard's investigations of failures, Osterberg's necessary redundancy in geotechnical engineering, and Apollonia's monitored decisions. Each of these 4 lectures emphasized that in all investigations, appropriate balance and reliance must be maintained on all aspects of the problem solution: field investigation, laboratory testing, theoretical studies, application of prior performance, and the utilization of judgment, frequently enhanced by personal intuition. Bill Lamb added significantly to this philosophical theme with his 1973 lecture on predictions in soil engineering. Now, Bill Lamb's ranking lecture was prepared from the standpoint of the professor, researcher, consultant, using as examples major projects with extensive investigations and large budgets, rather than from the perspective of the practicing geotechnical engineer, who must usually cope with an abbreviated time schedule, limited budgets, and a litigious environment. This paper is based more on routine performance predictions that are required of the geotechnical engineering consultant, confronted with a myriad of limitations in commercial practice. In a large measure, most of our commercial predictions are found to be acceptably close to actual performance, in that the deviation of performance from prediction is usually not sufficient to cause the client, the project user, a regulatory agency, or others to complain about poor quality of predictions. Despite our best efforts, however, our predictions occasionally miss the mark, and we're confronted by conformance that is significantly at odds with our best predictive efforts. We must carefully evaluate and openly discuss such projects whenever possible, since the majority of real leaps in our knowledge have been the results of well-documented analyses of performance and, unfortunately, of some major failures. The lessons to be learned are not only the technical calibrations from Class C1 after-the-fact predictions or from Jerry Leonard's failure analyses, but equally important, improved definition of the critical factors in the prediction process and improvements in our mental approach to predictions. I've been fortunate to have avoided being associated with catastrophic failures, although a number of my projects did not behave quite as I had expected. I will show by a series of examples, several from my own personal practice, performance that deviated from prediction, and will discuss the probable cause or causes of the variances. The discussion of cause will attempt to identify, when possible, the procedural defect in the predictive process with minimal effort to improve the technical aspects of the predictive method. The objective is to minimize deviations of predictions from performance by eliminating those defects in the process. I will also strive to emphasize the importance of judgment and intuition throughout the development of predictions. Another secondary objective will be to identify some kinds of predictions for which our success will be limited. Before we start with the examples, let us examine the critical elements that are part of the solution of most geotechnical problems. The geotechnical engineer must have, before he completes his prediction, gone through these 6 steps. First, he must have developed an adequate representation or modeling of the foundation stratigraphy, including the water level position, and an understanding of the regional and site geology. Second, developed an appropriate representation or modeling of the soil parameters that are critical to the particular problem. Third, selected an applicable theory for the analysis, and if stability is involved in the prediction, the factor of safety to be applied must be compatible with the soil parameters and the method of analysis. Fourth, he must have gathered and evaluated historical performance data on similar structures or problems in the area or in similar geologic settings. Fifth, must have utilized his judgment by questioning the applicability of the approach to the prediction and in critical review of the conclusions and the predictions. And sixth, judiciously employed gut feel or intuition in relation to the entire problem. These 6 elements are not independent of one another, but actually are very interdependent and must be compatible with each other, particularly number 2 and number 3. A great many of our numerical predictive techniques have been derived by empirical correlations, essentially Class C1 predictions, in which the soil parameters utilized must conform to those that are used in the derivation of the technique. A number of predictive techniques in the literature for clays, for example, rely on shear strengths determined by unconfined compression tests on ordinary, good quality, undisturbed samples. A potential error by an inexperienced engineer is to conclude that he or she should use the results from a quote, better unquote test method, such as the in situ vein, or perhaps special triaxial tests on highest quality piston samples, with the original empirical coefficients, and thereby obtain a better prediction. Unfortunately, he or she will usually be wrong. Elements 5 and 6, judgment and intuition, are most important. If a theoretical numerical prediction derived from 1, 2, and 3 differs from the engineer's judgment as applied to historical data, or even if intuition alone raises questions about the prediction, he or she should re-examine the numbers. Most of us are, or should be, familiar with Terzaghi's admonition that if theory did not match his expectations based on his experience, he would look for a new theory. I've adopted, for the sake of presentation, the concept that a circle can represent the range of presumed knowledge or understanding inherent in each of these 6 critical elements, and that the circle size represents the limits of accurate prediction. This graphical presentation is intended to be thought-provoking and intuitive, rather than fully appropriate or correct from a mathematical perspective. We will assume then that when all of the element circles overlap, the actual performance will be located in that overlapping area. Unfortunately, we won't know until after the structure is built and the performance is monitored whether the prediction was valid or not. Schematically then, each of the elements could be represented by a circle, not all necessarily of the same size, with bigger circles representing better understanding. In fact, the relative size of the circles will vary from project to project, and the individual circles will be strongly affected by the uniqueness of the site, the project, and the experience of the geotechnical engineer. I've shown only 4 circles rather than 6 to simplify the diagrams. But for a perfect prediction, such as at the bottom, all elements must be fully compatible, each must be valid and correct, and the process completed without numerical error. If all of the element circles overlap, as over on the left, our prediction will probably be satisfactory. But if the circles do not overlap, as over on the right, our prediction will not be satisfactory unless we achieve it by blind luck resulting from compensating errors. In the examples to follow, I will attempt to identify which element in the prediction process was off target, causing the prediction to deviate from the actual performance. 2 other conceptual ways of looking at accuracy of predictions as related to quality of method and quality of data were suggested by Bill Lamb. One is conventional wisdom. The better the data, the better the method, the better the prediction, as is indicated by the intersection of the dashed lines. At about a 50% quality of data, there's about a 42% accuracy of prediction. We go over to 90% quality of data, something in the order of about a 62% quality of a prediction. The second concept was an intuitive belief of his with which I agree. This graph suggests that the engineer must, quote, be consistent in the sophistication of his method of analysis and in the quality of the data. The dashed lines on this chart indicate again that at 50%, the quality of the prediction will be in the order of a little under 40%. But if we increase the quality of the data out to 90%, the accuracy of the prediction is dropped down to only about 20%. The dashed lines really show that for a given quality of analysis, improved quality of data will improve the prediction up to a certain point. Any further improvement in data quality will actually cause a deterioration in the prediction accuracy. The importance of these conceptual illustrations in my circles is that the engineer predictor, the ordinary geotechnical consultant, must apply his judgment by questioning the approach to the prediction, the validity of each element, the compatibility of the several elements, the appropriateness of the numerical procedure, and the basic correction of the final prediction. So let's examine a few examples. The level of precision required for a satisfactory prediction can be quite variable. As Ralph Peck pointed out many years ago, tolerable settlement may be governed by a factor as non-technical as paint color. He described a settlement problem for a Chicago apartment building. The predicted and observed settlements and differential settlements were all small, within the usual tolerances set by structural performance. But several of the occupants in the apartment building had painted some of their walls dark greens and dark browns. The fine hairline plaster cracks that would have been only slightly noticeable with light-colored paint were very obvious in the dark walls. So the normally tolerable settlement that produced only slight cracking of the plaster walls were intolerable for these building occupants. Definition of acceptable deviation of performance from prediction is an important but often overlooked part of the prediction-making process. The prediction must be presented in terms of that tolerance, rather than being stated like a computer printout with many significant figures. We must continually remind ourselves of the difference between precision and accuracy. The San Jacinto Monument at the San Jacinto Battleground near Houston was planned and built as a part of the 1936 centennial celebration of Texas independence and the decisive battle at that site that influenced Texas, American, and world history. The monument is 555 feet tall from the top of the 33-foot star all the way down to its base. The monument shaft and the museum around its base are supported on a mat 124 feet square, 18 feet thick in the middle and 5 feet thick at the edges. The net foundation bearing pressure is about 2,900 pounds per square foot. The original site investigation consisted primarily of 4 field loading tests on 17-inch square plates at the time of construction. These tests indicated an ultimate bearing capacity of about 16,000 PSF. In addition, there was one boring at the site during construction with 3 undisturbed soil samples from the top 20 feet. Now, the soil stratigraphy to a depth of 200 feet that was determined in 1953 is shown on this slide. Mostly stiff to hard clays with layers of dense sand. These soils are typical of the Beaumont Clay Formation, a deposit of Pleistocene age. Based on the tests from the original 1936 samples and stratigraphy from a nearby water well, Professor Raymond F. Dawson at the University of Texas estimated in 1938 that the ultimate settlement would be 7.35 inches and it would occur in 800 years. His time settlement prediction is shown by the dashed curve. It has the typical parabolic shape of classical primary consolidation of clay. The prediction was made just after the first International Conference on Soil Mechanics and Foundation Engineering, held in Cambridge, Massachusetts in 1936. Benchmark set about 275 feet northeast from the monument. The observations made over a period of 44 years yield the average settlement curve that's also shown on this slide. After 2 to 3 years, the settlement became almost linear, with a slight decrease in the rate in about the 1960 period. But the settlement continued to be linear. After 44 years, in 1980, the maximum settlement was 12.9 inches near the mat center under one edge of the shaft. The average settlement was 12.3 inches as shown here. The minimum was 11.6 at the northeast corner. Analysis of the last set of observations indicated a slight tilt north to south with no significant tilt east or west. Precision surveying of the monument's shaft that was done at the same time showed essentially the same tilt. The magnitude of the settlement and the shape of the time settlement curve as observed are obviously quite different from those predicted. Professor Dawson concluded in a 1984 paper that, quote, secondary consolidation may not have been included properly in the field curve, unquote. I'm inclined to agree, even though secondary consolidation is usually not arithmetically linear. In reference to the critical elements, the information available to Professor Dawson on soil stratigraphy and soil properties was insufficient. There were no historical data to guide his prediction or to influence his judgment. At the time, I doubt if any one of us would have disagreed with his prediction. In 1967, the Gerald E. Hines interest joined Shell Oil Company in planning for construction of the 52-story One Shell Plaza in downtown Houston to be designed by Skidmore, Owings & Merrill. Tenneco Oil Company had completed their 36-story office building in 1962, just diagonally across the street from the One Shell Plaza site. A senior vice president of Tenneco was concerned about the potential effects that construction of One Shell Plaza might have on his building. As the geotechnical consultant for Hines, I attended a high-level conference that included senior officials from the Tenneco, Hines, SOM organizations, and representatives of the contractor. In that meeting, the Tenneco vice president had a number of pointed questions. One of those questions was, what will construction of One Shell Plaza do to the foundation performance of our structure? I'd been a special consultant to the architect on the Tenneco building to supplement the work of EDCO engineers who were the primary geotechnical consultants on the Tenneco building, and consequently was generally familiar with the Tenneco foundation. But at that time, as a soil consultant on One Shell, I had not yet even made a crude analysis of what the offsite effects of One Shell construction would be. Well, the proposed shell building construction was to require a 60-foot excavation for the 132-foot by 192-foot plan in the middle of the structure, with a 50-foot excavation around the perimeter to fully occupy the 272-foot square block. As shown by this profile beneath the shell building, the water table before construction was at a depth of about 35 feet below grade, thus requiring construction dewatering to lower the water table at least another 25 feet around the deepest portion of the excavation. Actually, as much as 30 to 35 feet of water level lowering at the limits of the block was anticipated. In addition, a permanent groundwater control system had been planned to maintain the water level at a depth of 50 feet below grade, which made a permanent lowering of at least 15 feet. The building construction would result in a net positive foundation load on the mat of 750 PSF and a net decrease of 5,500 PSF in the annular area around the mat. The predictions of the effect of one shell on Tenneco were needed on the spot with no opportunity for analysis. My immediate answer to the Vice President's question was that the Tenneco building would tilt a little bit, but not enough that anyone other than a surveyor would know. The follow-on question was how much? The answer, probably less than 3/4 of an inch. As I remember, that answer was satisfactory to Tenneco, and the meeting went on to other Tenneco concerns. Before going on to the next slide, let me point out the location of two critical reference points, J1 and J18. J1 closest to the shell and J18 the middle of the side of the building the furthest away from it. Also to point out that there were 8 major columns supporting the exterior of the Tenneco building. McLelland Engineers was authorized by Hines to make movement observations of the Tenneco and other buildings in the vicinity. The surveys were initiated in mid-67 and continued at regular intervals for the next 4.5 years until well after completion of one shell in late 71. Our record of the differential movement between the column closest to the shell building, J1, and point J18 on the middle of the side furthest away is presented on this slide. The data reveal that the Tenneco building was actually tilting away from one shell in an amount of about 1/2 an inch by mid-1970. The number is not markedly different from that magnitude that it was estimated generally on the basis of judgment and intuition. The graph also shows that there was a rebound occurring for more than a year after the structural frame of one shell was completed in early 70. But load development on the one shell mat continued well on in until late 1971. But let me add a little more information on the Tenneco building performance. After we had begun our regular surveying and monitoring of the building movement, we learned that ETCO had been monitoring the building movement since its completion in late 62. Adding their historical data then, we get this record of the differential settlement for that entire period. But it also showed that the Tenneco building had been undergoing significant tilting early in its life prior to beginning of construction for one shell. Further, the graph shows that the rate of differential subsidence of movement increased only slightly after one shell construction began. Detailed review of the records for J18 and the other 4 columns on the south half of the block strongly suggests that the incremental differential settlement of Tenneco due to one shell was only about 1/3 of an inch. It's interesting to note that the total differential settlement for this period is 0.72 inches, coincidentally rather close to the 0.75 expected effect of one shell. This record might actually have been taken by some as verification of my off-the-cuff guesstimate rather than prediction of 3/4 of an inch. At this point, though, it's well to return to my specific prediction statement. Perhaps you realized I did not state to Tenneco which way their building would tilt. Prior experience with another deep mat foundation in Houston had shown to me that the stress relief due to the excavation would have a greater effect on an adjacent building than the water level lowering, and that tilt away of that adjacent building would occur. But I did refrain in the meeting from saying which way Tenneco would tilt. What I did not know was that the ongoing tilt was as significant as the effect of one shell construction would be. A quick explanation of the ongoing tilt is in order. Most of you are aware, I think, that Houston is undergoing area subsidence due to major water level lowering in deep aquifers. Actually, one of the many wells in downtown Houston is located under Tenneco in its southwest corner. It was installed to provide makeup water for their air conditioning system. The local subsidence, due to the local water level drawdown in the deep aquifers created by that well, most likely contributed to the tilt. Construction of the 1100 Milam building just south of the Tenneco building began in 1972, adding new impacts on the settlement record of the Tenneco building, completely obscuring the effects of one shell. Looking back, my first predictive answer was quite correct and appropriate. One shell would cause Tenneco to tilt, but not in a magnitude to cause any problems. The second part of the answer, putting dimensions to the prediction, was necessary to satisfy the technical background of the engineer vice president asking the question, but was admittedly without any precise support. I'm confident that Tenneco remembered only the general answer and believed that performance matched the prediction. But a purist could argue that the prediction was off target without any mention of direction. The slight mismatch of prediction from performance in this case can be largely attributed to the prediction really being a guesstimate, since there was no analysis. Also contributing to the mismatch, however, was the non-use of historical data for the structure, even though its availability was unknown to the predictor. The lessons to be learned are to make use of all available historical data available to the project and to consider all of the physical events having potential impact on the foundation performance. You must not overlook some construction detail or activity that might influence that structure performance. In planning for construction of petroleum development platforms in Bass Strait off the southeast coast of Australia, Esso Standard Oil Australia Limited had borings made at 5 sites by a local contractor over a period of about 3 years in the mid to late 60s. Logs of the borings and some of the samples were sent to us in Houston for evaluation and development of pile capacity curves. Soils at all of the locations were found to be granular, as shown by this boring log. The samples were retrieved by a procedure approximating the standard penetration test. The blow counts and the drilling records suggested that the granular formation was relatively dense and contained cemented layers, some more rock-like than others. These grain size curves are typical of all the borings in the area and many other offshore deposits. At some locations, the silt content of the sand was relatively large. The borings and the sample data were studied in our office for preparation for development of pile capacity curves for use by the structural engineer in his selection of pile lengths to be driven. We used our then standard procedures that we applied to piles driven into sands to compute pile capacity. Well, the piles for the first platform were driven in late '67. Those piles drove hard, which was attributed to the presence of the dense sand. The next 3 platforms were installed at about 6-month intervals, and their piles all drove relatively easy. This low driving resistance was attributed to the high silt content in the formation. The pile lengths were arbitrarily increased in the field to compensate for the lower driving resistance. Then in December of 1968, a blowout occurred at the Marlin platform, the second one that had been installed, creating a crater as much as 40 feet deep that encompassed the conductors and some of the piles. Concern about the reduced capacity of those piles due to the crater led to additional borings and pull-out tests on conductors at several platforms and a comprehensive load testing program at Kingfish A, which was the 4th platform. 6 pull-out tests were performed at Kingfish A on conductors that were 20 inches in diameter and driven to penetrations of 148 to 271 feet. These tests revealed that the average mobilized tensile frictional resistance was in the order of only 200 to 300 pounds per square foot. These frictional values are much lower than the average tensile skin friction value of 1,320 psf we computed in our analysis for 200 feet of penetration. From them, we concluded that the frictional capacity of the piles in place was only about 1/4 of what we'd originally predicted. Why? Close examination under a microscope of washed samples, washed components from sand samples from the new borings showed them to consist of calcium carbonate, not silica, like the sands that we were familiar with in the Gulf of Mexico and the North Sea. These particular grains are skeletal remains of marine organisms, relatively soft and crushable. These shapes are not visible to the naked eye. Some particles are coated grains, or ulis. All were within a matrix of lime mud or micrite. This is a thin section microphotograph showing individual grains with bonds in between and relatively large void spaces in between the grains, creating a relatively delicate and fragile structure, even though the original material may be hard and rock-like. It became apparent that when an open-end pipe pile is driven into these materials, the grains crush, the bonds break, and there is no buildup of lateral soil pressure and frictional resistance on the pile wall. Consultations with geologists and carbonate sedimentologists confirmed that the marine origin of these deposits resulted in a structure much different from that of the silica sands in the Gulf of Mexico and the North Sea, with which we were familiar. Immediately, emergency investigations were performed to evaluate this severe new problem, and very comprehensive studies were initiated on the capacity of piles in calcareous deposits. The first results were published in 1973 by Angermeyer and were followed by reference to the problem by McLelland in his Terzaghi Lecture. The results of studies undertaken worldwide to better understand marine carbonate deposits were presented in a specialty conference held in Perth, Australia in '68. The lesson to be learned from Bass Straits in the context of this lecture is that the simple extrapolation of a predictive procedure to a different geologic setting is fraught with considerable hazard, particularly without having closely examined the samples. Yet this is a risk that many of us run at one time or another in our career. Because of the empiricism of many of our predictive techniques, we must try every time to be sure that each aspect of our problem is compatible with those on which the predictive technique was developed. As a part of the 1989 Geotechnical Congress held at Northwestern in 1989, Richard Fino organized a predictive exercise focused on the actual capacities of an 18-inch pipe pile, a 14-inch H-pile, a cased drill pier, and a slurry-installed drill pier. All of the 4 foundation elements had 50 feet of penetration through 23 feet of sand fill and then on into a soft to medium stiff clay. All of the participants were furnished geotechnical data from the test site and were asked to predict a number of aspects of performance, including capacity at 3 different times after installation, load deflection curves, pore pressures adjacent to the piles during driving, residual loads, and capacity contributions from the 2 major strata. On capacity, they were asked first for a best estimate of the ultimate capacity, and then a, quote, lower bound estimate of capacity with a 90% confidence that the actual value would be higher than this lower bound, unquote. Predictions were received from 24 participating teams, but not all of the teams predicted everything. For this lecture, I am limiting my review and comments to the 2 driven piles and their ultimate capacity, nominally 1 year after driving, actually 43 weeks. Professor Fino, in his summary of the program, chose to use the maximum applied load as the ultimate capacity, and I will stick with his convention. The measured capacity of the two driven piles were quite similar, 220 kips for the H pile and 230 kips for the pipe pile. The predictors used a wide range of predictive procedures as documented in an ASCE special publication. The mean best estimate of ultimate capacity for each of the test piles were reasonably close to the measured capacities, 224 kips for the H pile and 215 kips for the pipe pile. Maybe what clients need to do is to hire 24 consultants for each project and average their predictions. Looking at the distribution of predictions for the H pile, 14 of the 22 predictions were within the range from minus 20% to plus 20% of the measured capacity, plus or minus 20%. The largest predicted capacity was 380 kips. The smallest was only 139, from 173 down to 63%. For the pipe pile, the largest predicted capacity was 370 kips, 161% of measured. The smallest was 126, only 55% of the actual. 11 of the 24 predictions for the pipe pile were within the plus or minus 20% range. It's particularly pertinent to note that for each of the two test piles, 10 of the on-target predictions were within the 80 to 100% range, right where most consultants would like to be, close to, but just on the conservative side of the actual value. Combining the results from both piles into a single histogram, there were 25 correct predictions, that is, within plus or minus 20%. These were made by 16 predictors using nearly that many different procedures. The conclusions that can be drawn are, first, on the average, the predictions were quite close. Individually, the deviation from measured was fairly large, from an under-prediction of 45% to an over-prediction of 73%. We'll take a look at those lower bound 90% confidence capacity values a little later in the discussion on factor of safety. I was not surprised that different techniques produce satisfactory answers. Also, I was not surprised that similar, if not identical, techniques produced both unsatisfactory and satisfactory results. Presumably, the predictions falling outside the acceptable range did not have proper judgment applied to the data interpretation to appropriately model the soil properties for the numerical model that was utilized. The interpretation of undrained shear strength of the clay that was used by the predictors ranged from 470 psf to 1,000. Obviously, such a wide range that some of the predictions would have to be substantially in error. Likewise, there was an equally large range for the friction angle of the sand from 28 to 47 degrees, with a tangent of the friction angle varying from 0.53 to 1.47. Perhaps each predictor's local experience played a part in producing these wide ranges. I wonder how much intuition was applied to the highest and the lowest predictions based on the predictor's experience. It's very important to emphasize that this situation is one in which a correct capacity prediction could occur due to two compensating errors because there was almost equal penetration in clay and in sand. Well, 19 of the predictors provided their estimate of the capacity contributions from the sand and the clay, a total of 38 predictions for the two piles. Out of these 38 combinations of predictions, there were 21 total capacity predictions that were within plus or minus 20% of the measured capacity. But of these 21 predictions, there were only 6 predictions of the relative contribution from the sand and the clay that were within plus or minus 20% of the actual relative contribution. This means that more than 2/3 of the correct values, correct total values, were correct because of compensating errors, some overestimating the capacity from the sand and the others from the clay, divided almost half and half. These results strongly suggest that for mixed soil profiles, right predictions of pile capacity may be produced by compensating errors in the contributions from the major soil components. Interestingly, there were two teams that were within plus or minus 20% on total capacity and on the distribution of capacity between sand and clay for both piles. The other predictions, time rate of capacity gain, pore pressures, residual loads after driving, load deflection performance, were generally quite scattered, indicating relatively low reliability. We cannot claim a high degree of individual reliability for capacity predictions for piles in mixed soil profiles, even though the bulk of the individual capacity predictions, 30 of them out of 46, were within the minus 30 to plus 20% of the measured capacity, a very desirable range. Perhaps we could even interpret the distribution of predictions as on this graph, particularly on the percentage side, as representing what a single predictor might expect for his predictions for a variety of piles in varying soil profiles. I would hope that application of judgment and intuition, those critical elements 5 and 6, would tend to eliminate some of the extremes, particularly on the upper side of this diagram. The major lesson to be learned from this example is that valid predictions may be derived due to compensating errors. We can also infer that extrapolation of local experience to a distant site may introduce deviations between predictions and performance. A wide range of conclusions on prediction reliability can be drawn from the results of the 1974 program to predict the failure height of the I-95 embankment test section near Boston. The program was conducted under the guidance of MIT for the FHWA, and it sought predictions as to the additional height of fill required to cause the test section on I-95 to fail. The existing section, shown in yellow, was about 34 feet high on the east with about a 1-on-1 side slope. There was a 1-on-1.9 side slope above a berm about 25 feet high on the west. The west slope was to be extended upward with slight steepening. The east slope would be steepened to the angle of repose of the sand fill, or about 1-on-1, as the embankment was raised, as sketched in red, over a distance of 300 feet in and out of the slide. The intent was for the east slope to fail, but not the west. The original foundation stratigraphy is typical of the Boston area, a few feet of peat underlain by a thin layer of well-graded silty sand. The foundation stratum of interest is the Boston blue clay, stiff and over-consolidated at the top, becoming soft and normally consolidated with depth. Now the upper surface of the basal glacial till slopes down from east to west across the site. And note the locations of the relatively significant instrumentation: slope indicators, piezometers, settlement plates, and heave markers. The participants were furnished detailed geotechnical data, including piezometer records, slope indicator deflection observations during the life of the existing fill, as well as comprehensive laboratory test results as shown. They were asked to predict the amount of additional fill to, quote, cause a stability failure, defined as differential deformation at the crest of a half a meter or more. They were also asked to predict movements indicated by the reference plates and inclinometers, and pore pressures recorded in the piezometers at various stages during the fill placement. The embankment failed at a height under the weight of 18.5 feet of additional fill, at a total height of 52.5 feet, both slopes failing early one morning with no one present. The failure was described as of being of extraordinary proportions. The crest of the test length dropped about 30 feet. The sides heaved up as much as 10. The length of the failure was 1,030 feet, extending 450 feet south of the heightened test section and 280 feet to the north. This photo is looking to the south. There was no warning from the slope indicators or piezometers or any other sorts of observations that there was impending failure. This slide shows a histogram of the ratio of predicted to observed additional heights to failure. The ratio ranges from 44 to 144%. 6 of the 10 predictors underestimated the incremental height, failure height, and 4 overestimated. According to Francisco Silva, who was closely associated with the exercise, the consensus of the participants and the audience at the exercise symposium was that the predictions varied quite widely. In another light, total height could be used as a basis for comparison of predictions with observed, because slope failure is really more related to the total fill height. On that basis, 7 out of the 10 predictions were within 13% of the ultimate height, even though different procedures had been employed. The range of predictions was from 41 to 60 feet, and the mean prediction was 49 feet, or 93% of the ultimate. The predictions of vertical and horizontal movements for the end of that period were considerably greater than had been observed. The average predicted movements were 3 to 10 times greater than observed, with very few predictions that were less than actual. Pore pressure predictions were a little closer, but the averages of the predicted pressure increments were 1.5 to 2 times those that were observed, even though there were a few predictions less than observed. Perhaps our prediction capabilities for movements and pore pressures have improved in 20 years, but I'm somewhat doubtful. One property value that was underestimated by the investigators and used by the predictors was the density of the additional fill. You may remember that the problem definition portrayed on an earlier slide gave the expected density of the new fill as 115 PCF. The actual measured in-place density was 122 PCF, an increase of 6%. Well, now the potential effect on the prediction histogram for incremental height to correct for this deviation would be to shift the ratio of predicted to observed by 6%. Not really very much in this case, but it is illustrative of the importance of accurately predicting all of the properties, not just the strength. The lessons learned from this predictive exercise fall more into the category of what we can or cannot predict with reliability. Total stability for the staged construction was reasonably well predicted. Incremental stability was not. Incremental pore pressures not too well as to their specific values, but good enough because of the very large initial pressures due to the existing embankment. Deformations were poorly predicted, with everyone, including the investigators, surprised by the lateral extent of the failure. The instrumentation did not give advance warning of impending failure as would be expected. The shape, limits, and specific location of the failure surface were relatively unpredictable. Jerry Leonard's, in his analytical review of the I-95 test fill in his Terzaghi Lecture, concluded that the designer of an embankment on soft clay, quote, must continue to rely heavily on experience within a given geologic region, experience that has been carefully digested in terms of local practice for site investigation, sampling, testing, and analysis. In none of the previous examples was safe stability an element of the prediction, so there was no consideration of factor of safety. Yet for most commercial geotechnical predictions, the consultant must complete his prediction process with a recommendation for an allowable load on a pile, an allowable bearing pressure for a footing, or an allowable slope for an excavation or an excavation for an embankment or an excavation of a given height. Let's look at the process of selecting a factor of safety to be applied to the computed ultimate capacity of a pile. The Northwestern pile exercise provides us with some guidance on what the participants viewed as appropriate conservatism to be applied in computing ultimate capacity, to which a factor of safety should be applied to obtain a safe working load for design. Professor Fino asked the predictors for their best estimate of ultimate capacity, their prediction of the ultimate failure load on the test piles, and that's what's shown on this slide. He also asked them for, quote, a lower bound estimate of capacity with 90% confidence that the actual value would be higher than this lower bound. While not stated, it was Professor Fino's expectation that this lower bound estimate would be the one that the predictor would use in a design assignment to which a factor of safety would be applied. Well, only 15 of the predictors provided these lower bound estimates. This slide is a repeat of the histogram of the best estimates for both piles, but with the 30 values from that group of 15 predictors shown by the cross-hatching imposed on the other diagram. The pattern, the medians, and the means of the group of 15 do not differ materially from those for the entire group. Consequently, then, we can use the lower bound estimates of the partial group to represent those of the entire predictor group. The upper histogram of the ratio of predicted to measured capacity is for the best estimate capacity of the predictor group of 15, with the inverted lower histogram for their lower bound estimates. Note that the median drops from 0.93 to 0.7. The mean drops from 1.02 to 0.76. Note also that there were still 3 predictors who had values that were 30 to 50% greater than the measured. 2 were for the pipe pile and 1 was for the H pile. Remember, these are predictions that were to have had 90% confidence that they would not be exceeded. Looking at the data another way to evaluate the degree of conservatism the predictor thought he was injecting into his lower bound analysis. This histogram is of the ratio of the individual lower bound capacity to the respective to the best estimate capacity. There are 2 values of 1.0 in this group of 6 for the range from 0.9 to 1.0, both for the pipe pile. These data suggest that the predictors would apply an average conservative multiplier of about 3/4 to their best estimate before applying a usual factor of safety. If they would have used a typical value of 2.0 to arrive at a working design load for these 2 piles, these design predictors would have achieved real factors of safety ranging from 3.7 to as little as 1.43. Another measure of perceived reliability of pile capacity predictions was obtained in a survey that was reported by me at the 1985 International Conference on Soil Mechanics and Foundation Engineering. One question was, in the state of present practice, 1984, how reliable do you consider the estimate of pile capacity to be in your practice? Nearly 25% of the respondents to that survey thought that their pile capacity estimates were valid to within plus or minus 10%. There was nearly another 30% that thought their values were good within plus or minus 20 to 30%, and about another nearly 25% didn't believe theirs were any better than to be within the range of plus or minus 30 to 50%. The results of this worldwide survey involving 56 respondents were not particularly different from the implications of the smaller Northwestern group, not a high degree of expected reliability. That paper also presented other discussion on choices of and approaches to selection of factors of safety for pile foundations. The choice of a specific factor of safety for a specific problem must be based on a relatively large number of considerations, which I've grouped into 4 categories: quality of strength data, appropriateness of analytical technique, type of loading, and consequences of failure. Under the quality of strength data, we're concerned about such issues as the volume or the amount of data, the quality of the samples, the adequacy of the test technique, and the amount of scatter in the data. Under appropriateness of analytical technique, we're concerned as to whether you might be using a new procedure, or perhaps a long, well-established procedure, or perhaps even multiple procedures in averaging the results. Is the procedure applicable to the geologic environment, and is it compatible with the strength data? Is the type of loading sustained, or maybe it's intermittent? Perhaps it's cycling, dynamic or seismic, or maybe it's a single event that will occur only one time during the life of the structure. What will the mode of the foundation failure be? Is the structure that it supports and the foundation system itself redundant? And then, of course, what's our confidence in the magnitude of the load? The consequences of failure include such concerns as would there be loss of life, a structure collapse, major structural damage, or only aesthetic damage. All of these considerations enter into the confidence level the predictor wishes to achieve. Some of the considerations are amenable to statistical and probabilistic analyses, but others can be approached only on a judgmental basis because statistical data are not available. Not included at all in any of these factors is the result of construction defects or construction quality. Many failures of pile foundations in particular are the result of construction defects rather than of design. But usually this uncertainty is not included in the factor of safety. Load and resistance factor design, LRFD, is rapidly taking over structural design of steel and concrete structures. It's also entering geotechnical foundation design, particularly for piles, as Professor Meyerhoff will be discussing some briefly. But all of my comments on conventional factor of safety are also applicable to the resistance factor to be included in an LRFD approach to structure foundations. The judgment of the geotechnical engineer that his factor of safety or resistance coefficient is fully compatible with all of the factors entering into the process, including the loads and the structure characteristics, is of vital importance. The experience of the predictor with the characteristics of the soil formation, the type of the supported structure, the economic and social consequences of failure, and all other factors must be taken into account, even if in a general, automatic, almost subconscious step in the mental process of the predictor. Before concluding, there's one additional point I'd like to make that deviates slightly from my theme. Good geotechnical engineering judgment requires a broad understanding of civil engineering in general. You must also have a good understanding of geology. But you have to be a good civil engineer first. You have to have an appreciation for structural design. The elements of civil engineering projects such as water supply, drainage, highways, bridges, waterfront facilities, dams, construction procedures, and the like. The geotechnical consultant must not lose sight of the fact that his technical solutions and predictions must be compatible with the remainder of the project and its constructability. There are several examples, or these several examples, have shown that predictions will probably deviate from actual performance when one or more of the critical elements of the predictive process is deficient or missing. This matrix of the 6 critical elements and the 6 numerical examples shows the major and minor causes of the mispredictions as I see them. Lack of proper judgment is a major cause in 4 out of the 6 examples. Inadequate modeling of the soil properties and inappropriate analytical techniques played a role as either a major or a minor cause 4 times in the 6 examples. We must recognize that it is often more important to know what we do not know than what we do know. Let's return briefly to the predictive process. My 6 critical elements could be considered as the steps within the process. In my opinion, however, an extremely first step would be missing. Therefore, I have added as the first step on this slide, outlining the prediction process, the application of sound judgment and perhaps intuition to the problem at hand, to select the approach to the prediction and to define the critical components of the process for the particular problem. The absence of this step may not have influenced the validity of the examples that I've just discussed. There are, however, many consulting assignments that would or could be adversely affected by the absence of proper judgment at their beginning. The other 5 steps are my 6 critical elements, with application of intuition included within the judgmental review of conclusions, predictions, and recommendations. I've talked about good judgment throughout this lecture. Where does good judgment come from? To paraphrase Mark Twain, who, when asked that question, replied, "Good judgment comes from experience." And where does experience come from? Experience comes from bad judgment. My advice is to try to rely on the bad experiences of others rather than your own. But good judgment is more than good technical knowledge. My advice to the young geotechnical engineer in particular is to read all of the Terzaghi Lectures and then the Dunnicliffe and Deere volume on Ralph Peck. Then make use, whenever possible, of all of the processes that are advocated within them: calculated risk, redundancy, monitor decisions, and the observational approach. There are 4 thoughts that I would like to leave with you. First, judgment must be applied throughout the predictive process. It must be applied at least twice, at the beginning and at the end of a numerical predictive exercise. Actually, it's necessary throughout the process. Second, every element of the prediction process is important. They are interrelated, and all must be compatible. Third, the prediction should be stated in terms compatible with the expected reliability without indication of more precision that it contains. And fourth, it's better to be approximately correct than to be precise and wrong. Thank you.
Thank you, John. John Focht has told me that he doesn't mind answering questions, and I would like to ask Albert Young to lead the discussion. He's a very enthusiastic and talented young professor. Albert.
Thank you, John, for such an enlightening lecture. As the discussion leader, I must take the advantage to ask the first question. In the 1985 International Conference, the late Professor Harry Seed made a statement in his opening remarks: 10 equal to a dozen. So I can, by the same principle, I can safely apply the same principle, saying your prediction of 0.75 inch total defensive settlement in your Tenneco case history equal to the 0.72 that you measure. I guess nobody will argue on that. As a young engineer, and I can safely pretend I belong to the group that you say the recent graduate who are computer literate. With the use of those great computers and all the sophisticated software, I don't think I can do better than you can. So at this point, I would like you to share your wisdom with the young engineers here. How do you get that number from your off-the-cuff estimation?
Can I tell you another story? Arthur Casagrande had a story that he always told in some of his classes, and this was about his involvement with one of the first very significant linear accelerators for the nuclear studies. And they got a group together, and the foundation engineers were saying the deflections or the movements were going to be this much, and the nuclear scientists said we can't tolerate but some other number. And they were way apart. They were worlds apart. So Dr. Casagrande and the chief scientist got together and sat down in a room, and Dr. Casagrande asked the scientist, "Where did you get your tolerable settlement from?" And he did, right there. He said, "Now you tell me, where did you get your estimate of the probable differential settlement?" And Casagrande said, "Right there." So that actually, I think Arthur also had some broad general experience and knew that it was about in that order. I did not actually have any experience directly related to a building, but we had in that earlier structure I mentioned measured movements of the curb diagonally across the building, across the street, and it was about an inch. And so I figured that the other far corner had moved a little bit, and so I just said less than 3/4 of an inch.
Okay, now any question from the floor?
From the precision of looking at the Northwestern exercise on piles and the I-95 MIT exercise, I don't see much difference in the precision of the bar graph that he showed. Yet we typically use 1.5 for slope stability and as high as 3 for foundations. Do you have any comment on those numbers?
I don't very often use 3 for a pile. My practice, I recommend 3 for a sustained tension load because I'm always afraid of that one. And I'm really ought to wait and answer that question after Professor Meyerhoff gets through, as he starts then to type it out. I think the difference is that in a broad sense, for most slope stability problems, we are tending to deal with averages. That is, you average out the shear strength all the way along. Yet usually for a pile or a footing, you are dealing with one individual element. Now, of course, there is averaging of a capacity down the length of the shaft. But I think there is a slight difference, and to me that there probably is a need for a slightly larger margin of uncertainty for the bearing capacity questions, because they're individual, unless you really had a very redundant structure, than for most of the excavation slope stability kinds of things. But I think as well it's an indication really of the composite experience of geotechnical engineers of wanting to have, they feel a little more comfortable with their stability computations of embankments most of the time than they are confident in their pile capacity or capacity predictions. And I think it's a reflection of that level of confidence. And you probably could achieve some further insight into that as a problem, maybe out of some of the things that they may have done in Canada as they were trying to go to LRFD, or looking at a survey on questions relative to slope stability.
John, I want to ask you about the embankment on I-95 in Boston area. Is any reason they don't build a side slope better than just 1-to-1 side slope on the embankment? You build an embankment 30 feet high, and then most time the embankment fail when you put on a steep side slope.
I didn't really quite understand the question. Why did they not use a steeper slope?
Flatter slope.
Well, they were trying to make it fail. I can't give you any background on the original cross-section, but they were trying to make this test section fail. There's a rather, that whole stretch of embankment was one of these political failures. That whole length of embankment in there was in place. There was a lot of other things done, and the politicians and the local populace got into, and they abandoned the location. And so this was not going to be finished. And so they excavated the material from another place along the abandoned embankment and used it to cause this one to make it fail. But this was a deliberate effort to make, they thought, one side fail, but both sides failed.
An objective of Lamb in his Rankine lecture and the I-95 symposium was to improve the profession's capability to make these predictions. I'm afraid after listening to your lecture today, I'm not sure in 20 years that we've really improved our ability to do the Class A prediction and before the fact prediction. Is that a correct assessment?
I think it depends upon which problem is that you're wanting to deal with. I think actually from the standpoint of pile foundations, I think from Jean-Louis' things generally on bearing capacity up here, I think most of the time on that set of documents, I think that the profession has a technical quality about like the histograms that you saw up there. It ranges to where if you did a normal factor of safety to it of 2 instead of 2, sometimes it's going to be down a little less than 1.5, and other times it may be up in terms of 3. I guess with respect to the I-95 embankment, and I'll stick my neck out, and I wasn't involved on it, I'll bet you that you could have done a better job of computing it on the basis of undrained strength than you could attempting to do it with a pore pressure analysis. I cannot verify that statement for you, but I did have experience with one other predictive exercise that was on some H-piles at MIT, or it was an MIT predictive exercise. I knew why they asked me, because they wanted me to have a pure practical sort of a prediction, so I really just about did mine on the airplane going up there on the back of an envelope. There were others that went through very extensive predictions, and when it came out, every one of us was wrong, but mine was as close as anybody else's. So I think really that the difficulty with I-95 was that there was the effort to try, they were working real hard. And I think it was a good exercise because we learned a lot from it. But I don't think that we are yet able to take a small sample into the laboratory, change its environment, even though you may go through a Sandshep process or anything else, and still produce something in that small sample, and that's a small sample, as to what happens within that total mass, a very large loaded area, and predict those pore pressure responses with confidence. Now, the analysis, I think, all do help a great deal in our understanding of the overall program, and I don't want to put that aside. I think it just is a matter we need to recognize where we can do predictions in which you ought to have a high level of confidence. I really believe that the people that were working on it still came up with answers that were appropriate for design. They just weren't as good as they wished them to be. I don't think we can predict pore pressures. I think we can predict stability.
As the time is running out, I'm going to take the last question. Then,
In your opinion, what's the major cause of that Tenneco building tilting? You mentioned about the stress relief
Okay.
of that one shell process.
When you dig a hole that is 60 feet deep, and one that's, then on the outside of that it's 50 feet deep, there's a very significant stress relief. So it's a negative load. And purely the elastic type response of the adjacent formation is the same as when you sit down on a bed and then you get up, the mattress comes up over some other place as well. And literally, there's one of the other buildings that was immediately across the street, and the data on that building was that it did this and it went back as the building was put back in place. So it purely is a response to the load removal in the excavation itself.
But you said that you still do the subsidence, the continuous subsidence of that.
No, the continuing tilting is due to the subsidence, and that's because as you have a well, you have a drawdown that varies underneath the building. And so you have more water level lowering on one side of the building than you do on the other, so there is a tendency for a greater stress increase on one side of the building than the other, and it causes it to tilt. It was, yeah, the well was off center. The well wasn't centered in the middle so that you had a uniform drawdown all the way across. So there's a differential load created by the water level lowering down at depth.